As we're talking about angular momentum and our principle of angular impulse and momentum, let's talk about one special case that doesn't come up too often for us, but may come up and is good to be aware of, and that's our conservation of angular momentum. So just like we have conservation of linear momentum, where we have our initial momentum equals our final momentum, we can have the same thing in angular momentum, where if our sum of our angular impulses is 0, right? So remembering that our initial momentum plus those angular impulses equals our final momentum. If this term is 0, if there are no external forces that cause a moment, right? No applied moments on the system, then our conservation of angular momentum says that our initial angular momentum is going to equal our final angular momentum. Right? This is our conservation of angular momentum. And where we usually see this is when we have a particle with no applied forces that or our applied forces, let me say this, or our applied forces that are parallel to our axis of interest, like the axis it's rotating about. Or they pass through that axis that it's rotating about. So for example, if I have, let's say here's an XY axis, here's a particle, and let's say it has an applied force on it, but that applied force is pointing towards the origin, right? And so if I do my angular momentum about this origin, this force wouldn't matter, right? This force is causing no impulse because it's causing no moment about that point, right? There's no moment when it passes through this point that we're rotating about, that point that we're finding the moment about. So this would be an example of where we could use conservation of angular momentum. Another one might be like, those big sky rides at like a carnival or a fair where they've got like a bunch of little seats that come off it and it kind of rotates around the center pole, right? Everybody's kind of like in a little seat, almost like a merry-go-round, but it's usually higher up in the air and you've got people who are in the seats and it rotates around that and the seats start to swing into the air. That would be another example of where we could use conservation of angular momentum. Because if we look at the riders here, we do a little, like a little zoom in free body diagram of this rider. For his free body diagram, he's got a tension that goes up to the pole. So we know that doesn't create a moment because it intersects with this axis of interest, right? This axis that we're rotating about. So this one doesn't cause any impulse. He also has a weight, which we know doesn't cause any impulse because it is parallel to this axis that we're rotating about. And those are really the only forces acting on him. So since both of these forces don't cause any moment, we could use conservation of angular momentum for that. So again, it's not a case that comes up too often, but when it does, we want to take advantage of it. So let's go ahead and look at an example of a case where we can use conservation of angular momentum. And oh look, our example has another amusement park ride in it. So in this example, we've got an amusement park ride that consists of a 200-kilogram car and passenger that are traveling at 3 meters per second along a circular path having a radius of 8 meters. And so if we look on our side here, I'm going to go ahead and just write down some info that they give us. So we've got our car traveling. We have that initial velocity of 3 meters per second. The mass is 200 kilograms. That's for the combo car and passenger. And then that initial radius there is 8 meters. If at t equals 0, the cable OA is pulled in towards O at 0.5 meters per second. And so at t equals 0, we start pulling this in Now this way has a velocity of 0.5 meters per second. Getting pulled inwards towards O, determine the speed of the car when t equals 4 seconds. Also determine the work done to pull in the cable. Alright, so this is a good candidate for our conservation of angular momentum, because if we look at this car and look at what's happening to our little amusement park car and passenger, is that there are no external forces on this. Right? There are no external forces that we can see. There's no force being applied. The only force that we know of is in the tension cable. Right? That is holding the car in place. It is being pulled in through cable OA, but that goes through our origin that we're rotating about. So because it goes through that point O, we can use our conservation of angular momentum. So let's take a look at these two conditions that they gave us. They told us that initially our car is out here. It has a velocity of 3 meters per second. And this radius is 8 meters. And then we want to find what that speed is. This speed here of the car, the tangential speed of our car, when t equals 4 seconds. So we know that because this thing is being reeled in, right, because they told us that cable is being pulled in at 0.5 meters per second, it's going to have a different length at that t equals 4 seconds. Right, so since it's being pulled in by 0.5 meters per second, then after 4 seconds, it would have been pulled in by 2 meters. So it's lost 2 meters of length there, meaning this cable is only 6 meters long now. This is t equals 0 at our t equals 4 seconds condition. And we're trying to find what that velocity is at that t equals 4 seconds. So since we know we can use that conservation of angular momentum, that's going to be our initial angular momentum equals our final angular momentum. And it's not a system of multiple particles, it's just the one single car. So R times M times V1 equals R times M times V2. Now our masses don't change, right? The mass of the car and the passenger don't change. The passenger doesn't like suddenly jump out or something. Everything is fine there. So we can discount those masses. Those masses will cancel out since it's going to be 200 either way. But it's very important to note that those radiuses do change. Those radii change from R1 to R2. So we've got to keep those in, and we've got to keep those accounted for in this conservation of angular momentum, where we have 8 is our initial radius times our initial velocity of 3 equals R2 is 6 times V2, which is what we're trying to find. So if I divide over that 6, I'm going to find that my final velocity is 4 meters per second. And again, that's that tangential velocity there. That tangential velocity is going to be that 4 meters per second that we've just calculated from our conservation of angular momentum. Now, bear in mind that it does actually have a speed along axis OA. It's being pulled in at that constant 0.5 meters per second. So we could find the overall magnitude of the speed by saying square root of 4 squared plus 0.05 squared to get the overall magnitude of the speed, because it's being pulled in one way and it has its tangential velocity. This is one of the few cases where we have a tangential and a normal velocity due to that rope being pulled in. So two separate things causing these velocities, and I don't think I actually, not in my notes, I don't know what our 16.25 square root, and that's going to give us 4.03 meters per second or the overall speed at t equals 4. So it depends on which one they're asking you for. This one is your tangential that we found, and then this one is your overall speed. So easy enough, right? Pretty simple to apply our conservation of angular momentum. You just have to have the right set of conditions to use it. Now our very last thing says determine the work done to pull in the cable. Determine the work done to pull in the cable. So anytime we're trying to find what that work is, it's probably a pretty good indication that we want to use our principle of work and energy. Now our energy isn't actually conserved here. Even though our momentum is conserved, our angular momentum is conserved, our energy is not conserved here. There is work being done from this pulling in of the cable. So just because we may have angular momentum conserved doesn't mean that we have linear momentum conserved, doesn't mean that we have energy conserved, right? It can be a totally different scenario. So here our energy is not conserved. And what we have is we have some work done pulling in that cable. So from our principle of work and energy, our initial kinetic energy plus the work done equals our final kinetic energy. So if I want to find that work done, I'm going to take my initial kinetic energy, 1/2 mv, or sorry, our final kinetic energy, 1/2 mv2 squared, minus that initial kinetic energy, 1/2 mv1 squared. And I'm going to plug those in to find the work done. So 1/2 mass is 200 times our initial velocity. That initial velocity was just 3. Why do I keep saying initial? I keep getting these backwards. This is final velocity. Sorry. And bear in mind, this final velocity is actually the overall final speed. So that 4.03 squared minus 1/2 times 200 times, now there's the 3, our initial velocity of 3, right, is before that 0.5 kicks in there. So the work done to pull that cable in I have is about 725 joules. Joules being our unit of work or energy in our SI units. So the work done to pull that cable in those, what was it, 4 seconds? In those 4 seconds, 725 joules.